Today, we're going to be going across the deepest parts of the ocean, trying to get from one island to the next. Remember, the only safe way to get from one island to the next island is to use the bridges that we have taught you in the previous units. Enjoy the ride. Hello, everyone. Today we're going to be going over the 40s. You're definitely going to need a calculator out and a periodic table. Today we're going to be going from Mole Island to Mole Island, and in the last unit we used subscripts, which are these little numbers like the 2 and H2O. But today and in this unit we're going to use coefficients, which come from balanced equations. And so we're going to be using the numbers out in front of the chemical compounds. So a lot of the work that we're doing today is very similar to what we did in the previous unit. We're just using coefficients instead of subscripts. So we're going to go over a few things. This unit is called stoichiometry. We break it down so you can pronounce it a little bit easier. In stoichiometry, we're looking at quantity of moles and the relationship of the reactants and products using coefficients. So in other words, we're using balanced equations in mole calculation problems. Or how much do I need of B to react with C? And so if you do get out into industry and you're trying to perform a chemical reaction for the company that's trying to make something, how much of this do I put in to react with that, and how much product will I end up getting out of? Coefficients are mole ratios. So coefficients are the numbers that are in front of compounds, and subscripts, these are like these little small numbers. Those are mole ratios as well. No matter what, though, subscripts and coefficients have infinite sig figs. And that's because water is always H2O. It's never anything else. And a balanced equation, it's only going to be balanced one way. And so therefore, it's going to have infinite sig figs as well. If you need to determine how many atoms there are in a molecule, you would try to answer this on your own. So if you're trying to find out how many atoms of hydrogen there are in H2O, you would use subscripts. And if you need to convert the quantity of one chemical into the quantity of another chemical, that means you'd have to use the balanced equation. You would be using the coefficients. So again, we are going to be going from Mole Island to Mole Island, and we're going to be using the coefficients to be able to do that, so our balanced equations. In 1 mole of water, which is H2O, there are 2 moles of hydrogen and 1 mole of oxygen. You should pause the video and answer the rest of these on this page, and then restart the video to see if you did it correctly. In carbon dioxide, di means 2, so in CO2, there are 1 mole of carbon and 2 moles of oxygen. Zinc acetate, so here's zinc, and zinc's got a 2 positive charge. Acetate is C2H3O2, and that's got a 1 negative charge, so I need 2 of these acetates to balance it out. There are how many moles of hydrogen? Well, this is like writing Zn C2H3O2 and have yet another acetate, C2H3O2. That's what this subscript of 2 is telling us. So in there would be 6 moles of hydrogen, and there would be 4 moles of oxygen. And in our last one, silver is Ag, sulfate is SO4. Silver has a positive 1 charge, sulfate has a 2 negative charge, so that means I need 2 of these silvers. There's no need for parentheses around the Ag. We only put parentheses around, like let's say we needed a couple of these SO4s or 3 of these SO4s, then we put a parentheses around it. But if it's just a simple element, we do not put the parentheses around it. So in this, there are 2 moles of Ag and there are 4 moles of oxygen. Balanced chemical reactions. For example, look at the burning of hydrogen gas. So when there are blank moles of blank burn, so what's burning in here? Well, oxygen is not burning. It's the hydrogen. So when, oh, not a 1, 8. When 2 moles of H2 burn, then 1 mole or moles of O2 are used or consumed. And then we get 2 moles of water that are formed. Again, pause the video at any point in time if you need to look at something a little longer, rather than just going at the speed that I am going at. When blank moles of blank burn, so what's burning here? This is what's burning. So go ahead and try to solve this, and then pause the video to do that, and then start the video back up. When 4 moles of Fe burn, then there are 3 moles of oxygen that are used, and then we get 2 moles of iron oxide that are formed. So this is rust. This is rusting. This is rust on your car. So iron comes in contact with oxygen and it makes rust. Write a balanced equation based on the following. So pause the video, see if you can do that. So 3 moles of hydrogen, so 3 moles of hydrogen gas. That's hydrogen gas. Remember, hydrogen is a diatomic element. It's always found in pairs. So 3 moles of hydrogen gas reacting with 1 mole of nitrogen gas. So that's N2. Again, nitrogen gas is another diatomic element. And that produces 2 moles of ammonia. And if you check that out, I have 2 N's on this side. I have 2 N's on this side. I have 6 H's over here. I got 6 H's over here, and we are in fact balanced. We're going to start seeing these little G's, little L's, and little S's in balanced equations. So we can see that right here. That's just telling you the phase of that element when the chemical reaction is occurring. So if a chemist was doing this, they could expect a lot of gas to be coming out of this particular reaction. When I say gas, I'm talking about things that are in the gas phase. So sometimes those letting us know if it's a solid, liquid, or gas comes in handy, and sometimes it doesn't matter. But you can start seeing that in more and more chemical reactions as we're working along, and I don't want that to freak you out. It says, how many moles of gas are produced when 2 moles of butane are burned? You're like, oh, I don't know what butane is. Well, is this butane? Nope. Is this butane? Nope. Is this butane? Nope. So what? Guess what? That must be butane. So how many moles of gas are produced when 2 moles of butane are burning? So 2 moles of butane, you get 8 moles of gas here, and you get 10 moles of gas here. So that's 18 moles of gas. Go ahead and try the next problem on your own and see if you can get the correct answer. All right, so how many moles of gas are burned with 4 moles? So if I double the moles of butane, then I would double the moles of oxygen that are used, and I should get twice as many carbon dioxide. I should get twice as many of these. So that's 16, and that's 20. So if we do the math on that, we end up getting 36 moles of gas that are produced. Use the mole-to-mole ratio, mole-to-mole conversion factor, and the reaction below to calculate how many moles of oxygen are made when 3.55 moles of potassium nitrate decomposes. So in all factor label problems, you start with the number that they give you. So they're giving us 3.55 moles of potassium nitrate. Well, you have to figure out which one of these is potassium nitrate. So this is potassium, and this is nitrate, so that's potassium nitrate. So mole KNO3. I put a multiplication sign. I put a division bar. Whatever this label is goes on the bottom of the next step. Those are our bare bones basics. So right now I'm at moles of KNO3. So I'm on one of the mole islands. And now I'm going to look and see exactly what it wants me to do. It says, how many moles of oxygen are made when 3.55 moles of potassium nitrate decomposes? So how much oxygen is made? And it wants moles of oxygen. So I'm going down here, and this is for O2. So this should be a one-step problem. So I can go to moles of O2. I look at this now when I'm going from mole island to mole island. It says use coefficients. That's the numbers in a balanced equation. And I look here and I see that there is a 4 in front of the KNO3, so I put a 4 in front of the moles of KNO3. I see a 5 in front of the oxygen, so I put a 5 there. And I am done. So now I do the math on that, and if I crunch all those numbers, I get 17.75 moles of O2. I look at my sig figs. I have 3 sig figs here. This is infinite. This is infinite. This equation cannot be balanced with different numbers. It's got to be those numbers. So those are infinite sig figs. So I should have an answer with 3 sig figs. And so that's 17.8 moles of oxygen would be produced when I put 3.55 moles of potassium nitrate into this chemical reaction. So that's what stoichiometry is. You're starting with one substance and you're finding out how much of another substance you could make or how much of another substance you would need. So let's go to the 45s, and we're going to do the first 2 problems together. The back side of the 45s, that will be the homework for the next day. So again, we are going to be using this mole island to mole island bridge. We're going to be using coefficients to get there. That's right here. If you don't know what coefficients are, maybe you want to write the balanced equation word right behind it, because that'll trigger that you have to use a balanced equation. A couple things that you do need to know about. There is no great way to go between grams and grams. We're going to start getting some problems that have grams and grams involved with them. So if you're doing gram island to gram island, you have to follow this pathway. There's no way that you can go from grams to grams. I just need you all to know that. You might want to actually do that in the future. All right, so here is our first problem. So it says we have 2.444 times 10 to the 24th molecules of hydrogen, and that will make how many moles of ammonia? So I want you to pause the video, see if you can set up the first steps. So with any luck, you were able to set up the first steps in this problem. You always start with what they give you. So we are going to start with 2.444 times 10 to the 24th molecules of hydrogen. Now, what kind of hydrogen? Well, in this problem, hydrogen is H2, so you're just going to assume that that's what we're talking about, is the H2. And it does say molecules of hydrogen, so that, again, that reinforces that it is H2. I put a multiplication sign, a division bar. Whatever this label is right here goes on the bottom of the next step. So this is molecules of H2. That's the bare bones basics that you should have done to start the problem. So in this problem, we're starting over here. We're starting over on molecule island. That's molecules of H2. And the only place we can go is to moles of H2. So that's going to be our next step. So we're going to go to moles of H2. We're just following that mole map that is on your cover. If we're at molecule island, the only place we can go to is mole island. So now we are on mole island. Multiplication sign, division bar, whatever this label that is on top goes on the bottom of the next step, moles of H2. And now I'm going to investigate. What do I have to do? It says we have that many molecules of hydrogen, 2.44 times 10 to the 24th molecules of hydrogen. And that's going to make how many moles of ammonia? This is my ammonia. So I'm simply just going down here. So this problem is one step bigger or longer than the previous problem. And this is going to be ammonia all the way down there. That's what that substance is. So I can go to moles of NH3. Putting in my numbers. So when I go from molecule island over to mole island, 6.02 times 10 to the 23rd, which is the mole number, is involved. 6.02 times 10 to the 23rd goes with the molecules, and the 1 goes with the moles. When I am going from mole island to mole island, it says use the coefficients. That means use the balanced equation. So there's a 3 in front of the H2, so I put a 3 in front of the moles of H2. There's a 2 in front of the ammonia, so I put a 2 there, and I solve the problem. I crunch those numbers. I get 2.7065, and you should always be crunching these numbers yourself to make sure that you're using your calculator correctly. Now I got to look at sig figs. This one has infinite because the numbers, the coefficients up there, that's exactly what they have to be. They can never be anything else. This is infinite sig figs. This is 3 sig figs, and this is 4 sig figs. So I should have a 3 sig fig number. So my answer ends up being 2.71. And then my last label that did not get canceled out is moles of ammonia, NH3. Now, if you want a prettier version, I'll look at that. I'll move that up for you. And you can take a prettier or better look at what I just did as well. Pause the video if you do, in fact, need to do that. So now we're left with the last problem that we're going to do today. It says you have 77.77 grams of iron 3 oxide. Was made from how many moles of iron? So it says it's telling us how much of this we have, and it wants to know how much of this did I have to put into it. And oxygen is coming from the air, so that's why we're not really too worried about that. So I start with the number that they give us, 77.77 grams of Fe2O3. Multiplication sign, division bar, whatever this label is right here goes on the bottom of my next step. Grams Fe2O3. So I'm right here, and everything in this top row is iron 3 oxide. So it's going to be grams of iron 3 oxide, moles of iron 3 oxide, molecules of iron 3 oxide. So that's where I'm starting. If I'm on Gram Island, which is right here, there's only one place I can go, and that's to mole island of iron 3 oxide. So I go moles of Fe2O3. Make sure you are absolutely using your mole map until this stuff sticks in your brain. I do not want my answer in moles of iron 3 oxide, so whatever the label is on top goes on the bottom of the next step. So moles Fe2O3. So now I am right here, mole island of iron 3 oxide. I need to go to a different substance. That's iron. How do I do that? I use the balanced equation to go from mole island to mole island. So I can, in fact, go moles of Fe2O3. Now, in the last, excuse me, I screwed that up. Moles of iron. Sorry about that, folks. Moles of Fe. Now, in the last unit, we used subscripts to get our answer, but in this unit, we're going to use coefficients. And we'll come back to this step in a little bit. Do I want my answer in moles of Fe? And I do, in fact. So I am done with this problem. I can put an equal sign. I'm going to go back and start putting in some numbers. So when I go from mole island to mole island, I use my balanced equation. I use those coefficients. So what number is in front of the Fe? This is a 4. So there's 4 moles of Fe. And what's in front of Fe2O3? That's a 2, so I put a 2 there. Like I said in the previous unit, we would actually look at that subscript to get how many irons there are in an iron 3 oxide, but in this case, we're using the balanced equation. I go to the moles in grams. So when I go from Gram Island over to mole island, I use the molar mass. And the molar mass of iron 3 oxide, folks, is 159.70 grams in 1 mole. So that's getting the mass of 2 irons and adding in the mass of 3 oxygens. I solved this, and I end up getting 0.97395. I look at my sig figs. Here I have 4 sig figs. Here I have 5 sig figs. Here I have infinite sig figs and infinite sig figs and infinite sig figs. So my fewest number of sig figs is 4. So my answer is 0.97340 actually, because this one's going to cause this one to round up, and that's what we would have for an answer. This is the last label. It's a label that does not get canceled out, so the answer would be mole Fe. And again, I will let you look at the prettier version of all that work that I just did to make sure you understand what's going on. So your homework is doing questions 3 and 4 on this page, and then the back side of this page will be done tomorrow. Have a good day.